Okay, today we're looking at our Acids and Bases chapter, chapter 16. Now, when we talk about this, what we're going to talk about mainly is our differences between acid bases and the properties as such, strength of them, and what's likely to tell you if it's a strong acid or base in the molecular formula. What does it mean to ionize? And then we're going to do some math with some pH and pOH values. And then we'll talk about buffers. Alright, so very first thing, our concentration and a type of acid. We have HCl right here. Now, this actually is concentrated. So even though it says 37%, this is actually a very highly concentrated. It's actually quite dangerous. It'll definitely hurt if you were to pour it on your hand. Even the fumes of this are actually pretty bad. When this opens up and you smell it, it actually kind of burns your nose even. Now, we do work with it. We have it in our chem lab. I typically don't let students come near it, but I will work on it mostly in the hood and sometimes just on the lab bench, but I do it in the back where the students can't be exposed to the vapor. But not all concentrated acids are dangerous like that. Vinegar can be found just as concentrated, maybe not as high of a percent or the same number, but it will be at a concentrated level, yet it's never really as dangerous as, say, hydrochloric acid is. Alright, so the main property of an acid is that they are, or the common properties of acids. They apparently have a sour taste. I'll take that from your textbook's word. I'm never going to taste any of these just to see and test that. I will agree that they are often corrosive. Most of our concentrated metals, if you were to put even a penny in with them, especially like the nitric acid, the HNO3, it would dissolve the penny. So it corrodes the penny down to just copper ions floating around in solution. Now there's plenty of other household acids that I would potentially taste. These, they're household. Might not want to bother with the vinegar. I'll trust that it's sour. But all these others I can taste. And while I wouldn't necessarily call them sour, the acidity part is similar. Alright, now that corrosion, what they're pointing out is that for most part, our high concentrated acids and many of our acids will react with certain metals very violently. So magnesium, for instance, if I put in with some HCl, I will get hydrogen gas. This is one of those single replacement reactions that we did ages ago, but it does actually release hydrogen gas as it breaks down. Baking soda will also do the same thing, and calcium carbonate. So if you were to get almost any of the rocks from outside here in Florida, this part of the state, and treat them with even 6 molar acid, so even the stuff you get for cleaning your pool, you will see that they will bubble up, and that's because the carbonates in there are being slowly converted into carbon dioxide. Alright, bases are actually going to feel slippery. Now that's not necessarily because they are slippery, it's just that you are full of oils and other fats and such, and just things that are naturally in our skins. And the sodium hydroxide, or the hydroxide in many of the bases, will actually turn your oils into soaps. So the reason it feels soapy is because it's turning you into soap. But all of them will kind of do that. So sodium, which is sodium hydroxide, which is lye, ammonia, and even baking soda, if you were to rub any of these on your fingers, it would feel slippery. Alright, our two main theories to explain acids started back in the 1800s with this guy Arrhenius. And he actually just said that acids were things that produced H pluses and bases were things that produced OHs. What he means by this: if I had that HCl that we were talking about and it bumps into water, well, he is saying that the H gets donated to the water to make H3O+, and then there's some Cl minuses floating around. But that is why HCl is acidic, because it makes us H3O. And he was pointing out that bases, like NaOH, when they dissolve in water, they just make aqueous ions of sodium and aqueous ions on OHs. And it's the OHs that make it basic. And that helped him explain why if you mix these two together, you just get water, which is why acids and bases neutralize each other. All right, but what it doesn't help us is why NH4 reacts, or NH3, sorry, reacts like a base, because NH3 is basic, yet it doesn't even have an oxygen in it. That was explained by this next theory. So Bronsted-Lowry theory talks about it's a proton transfer. What I mean by that, we might have the exact same equation for the HCl, but this Bronsted-Lowry theory saying is it's transferring the H to the water. And I know, doesn't change anything at all about the equation, it's just changing the terminology. What it helps though is on that NH3. So what we're going to say here is we're going to transfer an H from the water to the NH3 and make NH4 positive, and then the water turns into the OH. And since OH is what we need to make the base, this Bronsted-Lowry theory explains why NH3 is basic. It doesn't create the OH, it gives a place to allow the water to turn into the OH. Alright, so our Bronsted-Lowry acids, we actually can simplify them all with that HA. This is kind of funny. These two things should be over here because we have our acid and we have our base. And the H3O plus is the conjugate acid because it's where the H of the acid got transferred to, and this is the conjugate base. Alright, so which theory explains why NH3 is a base? That was our second one, which is that Bronsted-Lowry. Okay, strengths of acids. A strong acid converts 100% of its H's in like HCl here. It's saying that 100% of those H's get transferred into water. What we typically see on a balanced equation to make sure that we agree with that is just a single one-way arrow. Now this two-way stuff, because it's saying it goes 100% to completion, every bit of the H's get donated. Alright, right now it's easier to say there are 6 common strong acids, and these are the 6 that we would focus on. HNO3, H2SO4, HClO4, HCl, HBr, and HI. The weird thing is, any other acid, and this is true from almost anything you know, that's not on this list is what we're going to call a weak acid. What I mean by that, you notice how this HCl, HBr, and HI, it's missing HF? Hydrofluoric acid is a thing, but when hydrofluoric acid bumps into water, it doesn't completely turn into F- and H3O. It's a nice little two-way arrow where when it's all said and done, there's still some HF left over. It hasn't all been converted into H's, H pluses, and F minuses. And that is the big difference. A strong acid totally dissociates. It is definitely something we call a strong electrolyte. And a weak acid doesn't actually go forward. And all weak acids can be summarized with this single equation. You have a weak acid bumping into water, and it's going to be in equilibrium with making some H3Os and leaving the rest and having an equal amount of A minuses, or the conjugate base of the weak acid. Alright, examples of weak acids. Almost anything that we don't include as our strong acids that has the word acid could work in. So acetic acid, vinegar, is a weak acid. Carbonic acid is also a weak acid. Okay, other acids that we have to consider is there are some that are what we call monoprotic. Monoprotic does just mean that it has a single proton that comes off. We will actually see this written often as just H and A. A meaning it's an acid, H meaning it has one H to give up. And it does mean that there's a 1-to-1 ratio of H's to H3O's. And all of them will have a similar equation to what's written here. We'll be just changing whatever the A part is. And that happens on our strong acids and our weak acids. The only thing really different on a strong acid and a weak acid equation is the arrow. Strong acid has the one-way arrow. Weak acids have the equilibrium arrow, the two-way arrows. Alright, now, turns out there are other acids that have more than one proton. H2SO4 is actually diprotic. You sometimes see diprotics written as just H2A. And there are triprotics, which are H3As. Now, what that does mean is when it's all done, the diprotic acid and the triprotic acid just give more H's. So H2SO4 actually does this nice little two-step process. So H2SO4 first gives up an H and makes HSO4. And then that HSO4 comes down here, bumps into another water, makes another H3O, and now it makes SO4 2-. Now, even though H2SO4 is a strong acid, only that first step is a strong one. All the rest are going to be two-ways. And even on the triprotics, they're going to be, at most, there'll be one that's a forward reaction. The others are an equilibrium reactions. All right, strengths of bases. We typically see our strong bases are the ones that transfer 100% to OHs. They're really the ones that are soluble. So if we think back to our solubility rules, OH with anything in group 1 is going to be quite soluble. Therefore, those are going to be strong bases. Turns out calcium and magnesium are as well, even though they're in group 2, leaving those to be strong bases. Almost all of our weak bases that involve OH are just ones that don't dissolve very well. The other weak bases are things like NH3. Most nitrogen-containing substances that have just 3 things off the nitrogen are bases. And then some of our things like carbonates can behave as bases. Okay, so which of these is our weakest of these acids? Well, I know HCl, HBr, and HI are all strong acids. So HF is the only one on here that is a weak acid. Alright. Neat thing is, water itself can be an acid or a base. What I mean by that, we showed water acting as the source of the proton to donate to the NH3. Therefore, the water in this case was the acid. We also showed the other option where the H gets transferred to the water. Therefore, in this case, it's acting like a base. Well, if this is an acid and this is a base, we can mix them, acid and base, and cause it to transfer. The acid donates an H, makes the H3O. The base accepts that H, leaves an OH. Alright, and that does actually happen in pure water. It does actually have collisions that happen between water molecules, and it does actually occur. Now, to put it in perspective, at 25 degrees, the concentration of water is around 55 molar. So very high concentration of water compared to moles of water to liters of water. But these guys are actually both very, very small. So at 25 degrees Celsius, this is 1 times 10 to the negative 7th. And this is 1 times 10 to the negative 7th. Even the purest water will have that at 25 degrees. Now, it will change with temperature, but the nice thing is they're perfectly equal. And it does make sure that the pH, or the water itself, is still what we consider neutralized. Alright, but I just said that word pH. You've probably heard of that. Now, does anybody remember the pH of normal neutral water? Yeah, pH of neutral water is 7. That's actually where that 7 came from. that -7 is, or the exponent on our H3O concentration is the pH number, or close to it. Alright, so that self-ionization that gives us that 1 times 10 to the -7th is actually going to happen always. Now, it won't always be equal to 1 times 10 to the -7th, because if we actually add something that makes this go up, then there's no reason to expect it to still be 1 times 10 to the -7th. But we do see something kind of interesting. If we were to multiply the H3O and OH together, we get this 1 times 10 to the -14th, and it turns out that value is always constant. Or the H3O times the OH is always the same. So even if we increase the H3O, the OH will have to decrease to keep the product to be equal to this 1 times 10 to the -14th. That's going to make it very nice. So if I give you an H3O concentration, we'll always be able to solve for the OH, or vice versa, something like so. So if I were to say, I want you to calculate the H3O concentration from an OH concentration, we're just going to plug it in this equation and solve for it. Now, brackets there do mean concentration, so we are talking about moles per liter always on this. And we can do something like this to figure out to see what a calculation would look like. So I am actually wanting to get the H plus concentration from the OH concentration. Oh well, wait, misreading that. I wanted to get the OH concentration if I have 5 times 10 to the -11 molar H plus. Alright, so I'm using this equation, which, if you notice, are the exact same one. Just got to make sure we're doing it, or the math will be the same. Just make sure you report the number right. So in this calculator, I'm going to put that 1 times 10 to the -14th in like so. 1. The EE is times 10. So that says 1 times 10 to the -14th. And I will divide that by 5 times 10 to the -11th. And I get, I can add another 0, 2.0 times 10 to the -4th for our OH concentration. Now do practice that. Some of your calculators might not have that EE button. And watch this. So if I do this by just typing it out, 1 times 10 raised to the -14th divided by 5 times 10 to the -11th. Doesn't that look like it's the same thing? Yeah, but look what happens if I enter there. See, the exponent is different? The reason that is, what the calculator actually did was something like this. 1 times 10 to the -14th divided by 5, and then multiplied both of that by 10 to the -11th. So if your calculator has used the times 10, do both those in parentheses, then you don't have to worry about it. Raised to the -11th, close parentheses, and that works. Alright, but do look. If you have that EE, it saves you a lot of time. Or buttons to press. Alright, let's try another one of these. And gonna kind of look for a trend. Alright, one trend that can pay off quite a bit is to realize that these two exponents, the one what we determined, not that, the one that we determined and the one we started out with, always add up to -15 if these numbers are anything other than 1. If they're 1, they add up to 14. If they're anything else, they add up to -15. So, since this is -4, we know the H3O must be -11. And sometimes that can save you a lot of calculation, because if only one of those had a -11, I would have been done already. But I don't have that, so I will need to actually calculate. Well, I guess this one can't be, can it? That's +11. So it's got to be negative 11. So to solve this, I take that 1 times 10 to the negative 14th and just divide it by the 1 I gave you. 4 times 10 to the negative 4th, and we get 2.5 to the negative 11th. All right. Now, if I were to give you that, can we tell by looking at just those two numbers, the OH concentration and the H3O concentration, can we tell if it's acidic or basic? Turns out we can. We just got to figure out which of these two numbers is larger. In this case, negative 4th is larger than negative 11th, so that does say that there's more OHs. If there's more OHs, it is basic. Because that's all this means. Acidic means H3O concentration is greater than the OH concentration. Basic means OH concentration is greater than the H3O concentration. And this means they're equal. Okay, now more often than not though, we relate concentrations of acids to something called the pH. The pH scale just makes things easier because it ranges, and I'm going to write this, 1 to 14. Now, turns out that's not the only range. It actually can be a negative value. It can actually be negative 0.99, at least mathematically, and it can be 14.99, at least mathematically. But that 14 scale is beneficial. Now, all it means is somehow they turn that negative 7 into the 7. And that 1.0 does actually mean 0, 0. Alright, it is just a log scale. It's the log button on your calculator of the H3O concentration. So if I were to do log of 1.0 times 10 to the negative 7th, I get negative 7. So the actual equation we use is that. We flip the sign though. So since it said negative 7, we flip the sign. So if I wanted to actually calculate this, so the H3O of 2.1 times 10 to the negative 3, I would actually put that into calculator like so. So I take the log of 2.1 times 10 to the negative 3rd, and I get 2.67. That's where this came from. Now, if I ever need to convert pH back to an H3O concentration, we use this nice little equation. H3O is 10 to the negative pH. Now, that comes in handy on your calculator. So, if the pH is 2.68, on my calculator, I'll put in, so see on my calculator it has log buttons right there, and the secondary function is 10 to the x. If I hit secondary log, and then type in negative 2. I'll do this. I'll do the rounded thing. 2.68. I get pretty much the exact same number. 2.1 times 10 to the negative 3rd. All right. Now, biggest reason you use pH is because it's easier to say. pH is 7 is neutral, and that's much nicer than saying 1 times 10 to the negative 7th molar concentration of H3O. And we know pH scales to a degree. Anything that's low, lower than 7, is acidic. Anything higher than 7 is basic. Turns out you can handle quite a bit. So even 1 molar NaOH, yeah, it's going to feel soapy and slippery, but if you get that on you, it's just going to feel like soapy or slippery. Now, it's quite possible it's gonna penetrate enough that your skin would end up looking like you've been in the bath too long, so it's gonna prune up like it does when it's wet for too long, and it might potentially get on its surface what looks like calluses. Yeah, it's just turning excess oil and dead skin into soap. And even here at this other end, 1 molar of HCl, yeah, that's probably gonna be noticeable. It gets on your skin, especially if you have like a paper cut or a hangnail or something. But for the most part, you can handle contact with that small of a concentration. Yet its pH is 0. It's everything below that that drastically hurts. And obviously, if this gets in the wrong part of your body, because think about vinegar. Ever got vinegar in a cut? Yeah, you'll know it's on a cut, and yet its pH is probably closer to 3 or even 4. That's actually pretty low for vinegar. Most vinegar is closer to a pH of 4, and yet it still burns if it gets into like a cut. Alright, but that's how we calculate pH from the H3O scale. So let's give it a try. Let's calculate the pH if I give you the OH concentration. Alright, well, I can't do the log of this because to get pH, I need the H3O first. So I'm going to need to turn that into an H3O concentration. And then once I have an H3O concentration, I can make a pH. Now, I'm not going to write all that out. I'm just going to let my calculator do all the work. So how do we turn an OH into an H3O? Well, we use that 1 times 10 to the -14th value. Divide that by 1 times 10 to the -6. Notice how this is 1 on the nose? Means our exponents should add up to 14. This is going to be 1 times 10 to the -8th. Now that I have the H3O concentration, I'm just going to take the log of that value. And I get a pH of 8. Alright, now, got one I gave you the pH. We're going to first turn the pH into the H3O. And once we have the H3O, then we'll do the OH. So how do we turn a pH into an H3O? Our secondary function of the log to the -7.41. That gives us the H3O concentration. So we will take 1 times 10 to the -14th and divide by the H3O. And we get an OH concentration of 2.57 times 10 to the -3rd. Was it -3rd? -7th. Alright. Concept-wise, what does it mean to change by a pH unit? It does mean the acid is now 10 times stronger for each change. Where that gets really weird. To go from a pH of, say, 4 to a pH of 5, the acid's gotten 10 times less strong. But to go from 4 to 6, that's now 100 times less strong. Here's 10 and then 10 times more. So it's always a factor of 10. So these changes are quite exponential. Now ask about this weird thing called POH. Turns out POH is kind of neat. POH is just the negative log of the OH concentration. Very comparable to the pH. Matter of fact, that little lowercase p does mean the same thing. So we had P of, say, a car. That just means to take the negative log of the car. At least somehow mathematically, you'd have to take the negative log of a car. That's all that lowercase p ever really means when you see it in anything mathematical. Alright, but what this really helps out for us, I'm going to erase this. What would we get if we were to actually try to figure out what the pH plus the POH is? Because it does turn out they're a constant. The reason I know it's a constant is because the pH is the negative log of the OH, of the H3O. And this is, the POH is the negative log of the OH. We actually know that the OH times the H3O is equal to that KW. Or, how about some examples? What's the pH of neutral water? Turns out it's 7, right? Well, the OH concentration of neutral water is also that 1 times 10 to the negative 7th, so its pOH must also be 7. Here's something neat. What would be the H3O times the OH? Well, it is 1 times 10 to the negative 14th. What's the log of that value? Yeah, it's 14. Turns out pH plus pOH always equals 14. Now, it turns out had I introduced that equation, that makes this second one a heck of a lot easier to solve. So what I'm going to do with this pH, instead of converting it to H3O, I'm going to turn it into the pOH, and then into the OH concentration. So look how this goes in your calculator. So we start with 14 and subtract 7.41. We get 6.59. And now I'm just going to do the inverse log of the negative of that value. And get the same value. And even up here, could have actually calculated the pOH log of 1 times 10 to the negative 6th, and we got a pOH of 6. And since we want a pH, we just need to get the difference between this and 14. pH is 8. Alright, now pOH is a thing. You don't really get pOH meters, but it does actually exist as a measurable amount. And we have that wonderful relationship between the two. Okay, so strong acids are actually very beneficial on our math because of that nice one-way arrow. If you know the concentration of your strong acid, you know exactly how much H plus was produced. So if I have 0.01 molar HCl, it does mean there's 0.01 molar H plus in there. And if I know the H plus concentration, I just throw that into my log, and I get a pH of 2. So calculating the pH of strong acid is actually kind of easy. You just actually figure out what your concentration is and take the log of it. It ends up looking something like this. So what's the pH of a 0.054 molar HNO3? First question is that a strong acid? Yes, it is. So since it's a strong acid, I just do the log of 0.054. And this has a pH of 1.27. Alright, trying to trip you up here. Asks for a pH and then gives you a strong base. From the concentration of the strong base, I'm going to get a pOH. So a log of 0.01 isn't the pH, it's the pOH because that's what's being produced here. So in this case, the pOH is 2, therefore the pH is 12 because 2 minus 14 is 12. Alright, we don't really do that with weak acids. So the math gets a little bit harder, and it has a lot to do with the fact that all weak acids, when they bump into water, yes, they do produce some H3Os and some A minuses, but there's still quite a bit of the HA left. So 0.1 molar acetic acid, we can't actually just throw the 0.1 into the calculator and get it. So we will not be calculating the pHs of weak acids at all. That's not really until even Chem 2. So the only way we're going to calculate the pH is from strong acids and strong bases. Alright, let's see if we can go backwards or just put all this together here. So what's the pH of a solution that has an H plus of 3.9 times 10 to the negative 12th? Well, what's the pH? And I give you an H. we just need to take the negative log of that. So log of 3.9 times 10 to the negative 12th is 11.41. And the next one, a base has a solution, a basic solution has a pH of 9.8. What's its molar H3O concentration? Alright, I'm going to work backwards here because I give you an H, a pH. So inverse log and put in negative 9.8 gives me an H3O concentration, which is what we want, of 1.58 times 10 to the negative 10th. Okay. Don't know why I have that again. Alright. The ways we go about getting pH measurements, there's really just two. Litmus paper and dyes can actually be kind of combined into one thing. Dyes really are. They used to have little medicine droppers, and you put things in and they change color based on the pH. And you still see that some. Most pool testing chemical kits that you can buy, some of them have little dyes. You put it in a little solution, you compare the color. But litmus paper is getting a little bit more common even on pools. You have little dip strips that you put in there. Very rarely do we have pH meters for pools. pH meters are typically more for a chemistry lab. All right, now, examples of what these look like. Litmus paper, there are different types of indicator paper. This one, as you can see, has different colors based on what it looks like, and that's what they're doing. They're dipping it in there, and the colors kind of tell you what the pH actually is. And we do have them that go all the way up to 14. I mostly use red and blue litmus paper. Red and blue litmus paper. Red paper turns blue when it's exposed to base, and blue litmus paper turns red when it's exposed to acids. And when it's time to clean up a lab, if I see a spill on the counter and we were messing with stuff that was potentially dangerous, I'll put my 2 pieces of litmus paper in there to see if it's something I need to worry about cleaning up. Because if it turns really bright red or really dark blue, I know it's a strong acid or a base, or potentially, and then I clean it up slightly different. But they're not super accurate if we want to get a real hard number. This is more of how bad it will burn if it gets in contact with you type of a test. If I want more accurate, I get a pH meter. Now, it's a probe. The reason these are a little bit more expensive is on this probe there is a glass membrane that's really incredibly thin, very easy to break. And that allows just the protons to transfer across. It creates a little bit of electrical current. So this is measuring an electrical current being generated. And then it's converted into the pH. But far more accurate. And we do get a chance to use these some in labs. At least in later classes. Alright, so reactions of acids and bases. For the most part, acids will react with what we call active metals. Now there are quite a few that are active, there are some that are totally inactive, and the activity scale comes in handy because it turns out iron, steel, is one that's right on the edge of being active. What that translates to, it will react eventually with water because water does have acids in it. And by react, it does actually turn into rust. Alright, so what do we do to keep metal from rusting? Well, we keep it protected by covering it with paint. The other thing we can do, like inside your water heater, for instance, so go draw a picture of a water heater. Inside there, along with the tubes to fill it up with water, somewhere in there, mostly on the top of them, there's just a rod. And it's typically made out of zinc or magnesium. It's a magnesium alloy. They actually, if you go to the hardware store, you can see sacrificial anodes or anode rods. And all that is, it's a metal that's more active. What that does is if it's in electrical contact with the metal container, the metal doesn't rust, but that anode rod does. And as long as it's there, the metal of your tank will not rust with the water because the acid in the water will go with the most active metal first. Alright, we also know that acids react with hydroxides. That's acids and bases. And the other one that we saw already, acids with carbonates, and even bicarbonates like baking soda. So carbonates is where they put it on the rocks and the rocks will bubble, and bicarbonates is vinegar with baking soda. So the 5th grade science fair project volcano, those are types of reactions. Now technically these are all types of neutralizations. The acids are going to be neutralized in all 3 of these reactions. Alright, so our first one that we're looking at in a little bit more detail is the straight acid-base neutralization reaction. Now we've seen this one before. Neutralization is always going to take an acid and a base, make water, and then a salt. And back when we first introduced this, we talked about complete ionic, total ionic, and net ionic. And the net ionic for all acid and base equations is going to have the H plus and the OH, H plus and OH, forming just water. Carbonates always do the same thing when they get exposed to strong acids. Actually even happens with many acids. We take advantage of it in antacids. So there are antacids that we take to help acid reflux that are made out of carbonates. When that tablet gets into your stomach, it does actually form CO2 gas bubbles, can cause you to belch or eventually come out as gas, might get absorbed by the body. But the CO2, as it's being produced, is actually turning the excess acid into water. So it is neutralizing the acids. But it's much funner to do this when, like with baking soda, so pour some acid on baking soda and get the nice little science fair project volcano going. Alright, other antacids, many of them are hydroxides or carbonates. They're just playing around with the solubility. Now Alka-Seltzer is a little bit misleading because you don't actually ever put that tablet straight into your, you don't eat the tablet. You're supposed to take those tablets and dissolve them in water. That actually creates a tonic solution along with the other stuff in there that helps your excess stomach in your belly. But all these others are slightly less soluble carbonates or hydroxides. Okay. Last little thing we introduced in this chapter is the concept of buffers. Now, buffers are solutions that resist changes to pH when you add H's or OH's. So what that means is, if it's got a pH like your blood of around 7.4, if you did something to add acid to it, you don't expect the pH to change very much. If you did something to add base, you don't expect the pH to change very much. They buffer the change of adding H's and OH's. Alright, they do this because they are a combination of a weak acid and its conjugate base. An example of that, one of our weak acids we introduced was acetic acid, C2H3O2. Its conjugate base is just C2H3O2. Well, it turns out if I take some of this and some of this, let's say it's equal amounts, so I got 1 molar of this and 1 molar of this, and I mix them in equal amounts, that's going to make a buffer. That buffer, turns out in this case, this buffer has a pH right around 5. And right around 5, if I add acid to it, all the acid gets neutralized by the base floating around there. And if I add base to it, it all gets neutralized by the acid going in there. And the pH stays relatively the same. It will change ever so slightly, but it's a very small change. Now, I can use different acids and their conjugate bases and get different pHs. So that's how they fine-tune these buffer solutions to whatever pH they want. They change which acid and which base. And if I want a basic one, I use a weak base and its conjugate acid. But they have to be pairs. So whatever we have here needs to be there without the H. And technically, I wrote up here acetic acid, and it says this is acetic acid here. They are the same thing. They've just got the formulas written differently. Okay, so, and this is what's going to happen. If we start with those equal amounts of those two, and we add acid, the acid will totally go away, and the acid portion of this one would get higher, and the base one would drop ever so slightly, because that extra acid, H's, are getting put onto there and shifting this over here. But all the H3O is now gone, the pH is still controlled by this acid and this base. If I come over here and add base, the base is going to get neutralized with these acids, meaning that the CH3COOH drops, and there's now more CCOO minus. But again, because it's all neutralized, the pH doesn't change very much. Alright, fortunately, we're not going to do math with these. To actually answer any questions we need to know about buffers, we're going to ask ourselves two things. We're going to make sure that the acids are conjugate pairs. Now, we have to watch out for the pairs. See these first two? They look like they're almost the same thing. It would almost make you think that H2PO4 minus could be a conjugate pair with PO4 3 minus. And not officially, not on paper, because they're not conjugate pairs. There's no single equation that will turn H2PO4 into PO4. It needs to go through the HPO4. So when we're talking about buffers, the pairs can only be different by a single H. So H2PO4 could be paired with HPO4, and HPO4 could be paired with PO4. Alright, the other thing we have to watch out for, a buffer that looks like a buffer, I'm going to write this out, H2SO4 and HSO4 minus. Looks like the only thing different is an H, but the reason this one can't be a buffer is because this one here is a strong acid. And strong acids don't form buffers, have to be weak acids. Now, that's sulfuric acid. If I had actually changed this to sulfurous acid, H2SO3, that one can actually form a buffer because it's now a weak acid. Alright, the other thing that we talk about with buffers is that they have a capacity. What I mean by that, they actually only work for a certain amount of time while the acid's in there. I'm going to back up to the weird chart. As you can probably imagine, I could keep adding H3O. As I add more and more H3O, it's going to react with more and more CH3COO minus. And this is a finite amount. Eventually this will go to 0. Once it goes to 0, all the extra H3O is going to actually cause the pH to drop. So what that would look like is, if I'm going to start here at a certain pH and slowly add some acid to it, we would actually see the pH gradually drop as more and more of this gets neutralized, and then suddenly we'd have a steady drop. Once the capacity for the buffering has ended, we'll start to see a much more rapid drop because of the increase of H3O. Well, that buffer capacity is based on the concentration. So I said we want these to be equal concentration. Well, if we make them equal at 1 molar or 5 molar, they both start with the same pH. But the one made with the 5 molar is going to resist the change longer because there's more components of that buffer. So buffer capacity is just related to the concentration. More concentrated your components are, the greater the buffer capacity. Alright, that finishes up with our acid and bases. You have plenty of practice problems. Send me any questions if you have any.